These hypothetical stars, more like Gravastars than ordinary black holes, don't have infinite density singularities at their centers. Instead, they feature a strange balance between matter and vacuum energy, leading some researchers to suggest that black holes may not be black holes at all, but rather massive dark energy reservoirs. This bold conclusion, however, didn't go unchallenged. Astronomers quickly fired back, arguing that the analysis of observational data wasn't rigorous enough. On the other hand, theoretical physicists raised objections, stating that the expansion of the universe should have nothing to do with the localized growth of black holes. Still, the idea that dark energy could exist in the form of gravastars remains scientifically tantalizing. If confirmed, it would be a game-changer, not just for our understanding of black holes, but for the entire framework of cosmology. Yet the scientific community won't be swayed easily. This theory needs better data and more compelling theoretical models. Until then, it remains a possibility, but not a consensus. So where do you fall in this debate? If it walks like a black hole, talks like a black hole, and swallows everything in its path, should we just call it a black hole? Or should we seriously consider the possibility that black holes might be secret troves of dark energy, holding the key to the universe's accelerated expansion? Let us know your thoughts and questions in the comments below. And while we're on the subject of stellar mysteries, if you're a long-time viewer of Infinity Beyond, then you probably already know. Betelgeuse is no ordinary star. It was a clear night when John Birmingham looked up at the stars with a sharp eye. He scanned the sky for familiar constellations, just as he had done countless times before. But when his gaze reached the Northern Crown, he stopped, stunned. There was a new bright star in this well-known constellation. What Birmingham had observed was a recurring nova in the binary star system known as T Coronae Borealis, affectionately nicknamed the Blaze Star. It was a once-in-a-lifetime astronomical event, and now, more than 150 years later, we may witness it again. This event shaped the field of stellar astronomy and revolutionized how we understand novae, powerful explosions in binary systems where a white dwarf steals matter from its companion star. And for those of us alive in 2024, we may be about to see that exact same blaze again. You won't even need a telescope. So, why is it going to happen again? When can we expect it? I'm Alex Molan, and you're watching Infinity Beyond. Join me as we prepare to observe this extraordinary stellar event, something so rare that only a few humans in history have ever seen it. T Coronae Borealis is what's known as a recurrent nova, a type of binary star system where nova eruptions occur multiple times over centuries. Unlike a supernova, which marks the end of a star's life, a recurrent nova survives each outburst. The system consists of a white dwarf and a red giant locked in a gravitational dance. Over time, the red giant loses mass to the white dwarf through accretion. When enough hydrogen accumulates on the dwarf's surface, a thermonuclear explosion is triggered, releasing a burst of light and energy, visible from Earth as a new star. Historical records and current models predict that the next eruption of T Car B could happen in mid to late 2024. And yes, this would be visible with the naked eye. No telescope, no observatory, just your eyes, a dark sky, and a moment of astronomical history repeating itself. Much of the material surrounding this particular star is part of its ejected mass, being shaped and sculpted by intense stellar winds. One day, this star will become a Wolf-Rayet star, a type of massive star millions of times more luminous than our Sun. However, right now, it's so hot that it's invisible to the naked eye. Most of its radiation lies in the ultraviolet range, far beyond our visible spectrum. But now let's step beyond our own galaxy. Number 42, NGC 49. So far, all the stars we've explored have been within our Milky Way galaxy. Observing individual stars outside of it is extremely difficult due to distance. But every once in a while, a cataclysmic cosmic event occurs, so energetic, so massive, that we can detect it from millions of light years away. That's exactly what happened in NGC 4993, a galaxy about 140 million light years from Earth. In August 2017, scientists at LIGO, Laser Interferometer Gravitational Wave Observatory, detected a gravitational wave signal, one unlike anything before. What followed was extraordinary. Within just 12 hours, astronomers located the optical source of the wave, the collision of two neutron stars. This wasn't just a supernova, it was something even rarer, a kilonova. Kilonovae occur when two ultra-dense neutron stars spiral together and merge, creating an explosion so powerful that it literally forges heavy elements like gold and platinum. Yes, you heard that right. The gold in your jewelry could have been created in an ancient kilonova. The explosion from NGC 4993 was visible across multiple wavelengths, from X-rays and gamma rays to visible light, and it marked the first time in history that astronomers were able to observe both gravitational waves and light from the same cosmic event. It was the beginning of a new era, multi-messenger astronomy, out of fuel and transforms into a red giant. But today, we're not just going to talk about the stars we're familiar with. Instead, we're going to contemplate stars we've never seen before, ones that astrophysicists say could hypothetically exist, including stars that are quite literally made of vacuum. I'm Alex Milan, and you're watching Infinity Beyond. Join me today as we dive into the world of exotic stars. Some of these stars can mimic black holes and resemble dark energy, which is why they have been the subject of many recent studies and even some sensational drama in the world of physics. In this video, we're going to explore all of it, from the physical theories at the core of these ideas to the wildest speculations surrounding them. But first, we need to lay some groundwork and understand how stars work in general, starting with the most important star of all, the Sun. Since the Sun is made of gas, or more specifically plasma, and not solid matter, you couldn't stand on its surface like you would on Earth. The Sun's surface gravity is about 28 times stronger than Earth's, meaning if you weighed 70 kilograms on Earth, you'd weigh nearly 2,000 kilograms there. But don't worry, you wouldn't get a chance to feel that weight. The Sun's intense heat would vaporize you instantly. So, how does a star like our Sun actually work? At the core of the Sun lies nuclear fusion, a process where hydrogen atoms fuse into helium, releasing tremendous amounts of energy in the form of heat and light. This fusion process is what balances the star's immense gravitational pull. If fusion stopped, gravity would cause the star to collapse in on itself. The life of a star depends on its mass. The more massive the star, the shorter its lifespan, as it burns through its fuel more quickly. Our Sun, being a medium-sized star, is expected to live for around 10 billion years. Right now, it's roughly halfway through its life. But stars much larger than the Sun end their lives quite differently. Some collapse into white dwarfs, others become neutron stars, and the most massive ones end as black holes. However, today, we'll go even further, beyond black holes, beyond neutron stars, to explore hypothetical stars that might exist only in the realm of theory, but perhaps one day will be observed. Asking about stars that physicists like Buchdahl would call less realistic. Let's imagine. What if a star were made of matter that allows for pressure to be negative in some regions and positive in others? In such a case, Buchdahl's limit wouldn't apply, and that star could be smaller than 9/8 of its Schwarzschild radius. In fact, it could theoretically be arbitrarily close in size to a black hole of the same mass. As a side note, theoretical stars like these, that mimic the appearance of black holes, have become quite a nuisance for astrophysicists. Why? Because now, every time they discover something that looks like a black hole, they can't just declare, "We found a black hole." Instead, they have to qualify it. It's either a black hole or a very compact object that mimics a black hole, even though, in their hearts, most of them are convinced it's a black hole. But back to our main point. What would these exotic stars, with negative pressures and bizarre densities, even look like? The answer is even stranger than you might guess. The Tolman-Oppenheimer-Volkoff equations, which extend the equations of stellar structure into the realm of general relativity, allow for some exotic solutions when you plug in hypothetical states of matter. One such solution results in a strange star known as a gravastar. Gravastars, or gravitational vacuum stars, are composed of a shell of matter surrounding a vacuum with negative pressure, like the energy density associated with dark energy or the cosmological constant. Think of a gravastar as a kind of cosmic bubble, where the inner region is like a balloon filled with vacuum energy and the outer shell prevents collapse. From the outside, it would appear nearly identical to a black hole. It would warp light, have a strong gravitational pull, and might even produce similar X-ray signatures. The major difference: gravastars don't have event horizons. That means, in theory, light and information could still escape, albeit under extreme conditions. And then there's an even weirder possibility. Dark energy stars. Hypothetical stars powered not by fusion, but by exotic energy fields that behave more like the mysterious force accelerating the expansion of our universe. These concepts challenge our very understanding of matter, gravity, and space-time. While they remain speculative for now, scientists continue to study these ideas using both mathematical models and astronomical observations. She spreads out her arms across the night sky, and if the sun were 10 times heavier to match the mass of Betelgeuse, its rotational velocity would drop dramatically to just 0.2 meters per second. That's the general rule. The larger and heavier a star is, the slower we expect it to spin. And yet, Betelgeuse defies all expectations. So what's going on here? One possible explanation is both fascinating and slightly terrifying: stellar cannibalism. Yes, you heard that right. Even though Betelgeuse didn't start out with this much angular momentum, it may have gained it by devouring another star. Stellar cannibalism is the term scientists use when one star eats its companion in a binary system. In more technical terms, the dominant star's gravity slowly pulls away the outer layers of its companion, layer by layer, until all that's left is a dense core. This stolen gas brings with it a large amount of angular momentum. So not only does the main star grow in size, it also begins to spin faster than it otherwise would. Could this be the true origin of Betelgeuse's unusual spin? Or is there something even more mysterious going on? Some astronomers believe Betelgeuse may be hiding secrets beneath its surface: unusual internal structures, turbulent magnetic fields, or perhaps even exotic particles affecting its behavior in ways we don't yet understand. Whatever the explanation, one thing is certain: Betelgeuse is not your average red supergiant. It's a ticking time bomb, a star that could go supernova at any moment within the next 100,000 years. When it does, the explosion will be visible from Earth even during the daytime. The night sky will shine brighter than it has in millennia. So next time you look up and see that reddish star in the constellation Orion, remember, you might just be looking at a cosmic predator, hiding its final surprise. In recorded history, one of the most famous instances of a stellar explosion was in 1604, when the German astronomer Johannes Kepler documented a supernova so bright it could be seen during the daytime. Imagine that, a new star appearing in broad daylight. Now, while the event we expect in 2024 isn't a supernova, It's anticipated to be one of the brightest classic novae of this century. Just like a supernova, it's a rare and remarkable occurrence. But unlike supernovae, which mark the death of a star, classic novae are more like cosmic outbursts that leave the system intact. In fact, classic novae that are visible to the naked eye occur relatively frequently, at least compared to supernovae. But here's the catch. Even though one happens roughly every year or two, they're usually not bright enough for the unaided eye to spot. But the blazed star, T Coronae Borealis, is different. Its expected outburst in 2020 could make it one of the brightest classic novae to appear in our sky in over 50 years. In astronomy, we measure a star's brightness as seen from Earth using the apparent magnitude scale. Here's how it works. The lower the magnitude number, the brighter the object. A star with magnitude 0 is brighter than a star with magnitude 1. The full moon, for example, has an apparent magnitude of about 12.7, while Venus at its brightest hits 4.7. T Coronae Borealis is predicted to reach a magnitude between 2.0 and 0.0, placing it in the top 20 brightest stars in the night sky during its peak. In practical terms, that means millions of people across Earth will be able to see it without a telescope, just by stepping outside and looking up. A cosmic firework, visible to the naked eye, happening in our lifetime. And if that's not something worth watching for, what is? Now let's take a look at some of the most special and peculiar stars ever recorded. And believe me when I say, some of these are absolutely breathtaking. Number 35, HH34 that did a spectacular sight, found near the Orion Nebula, is known as a Herbig-Haro object. It's an emission jet from a very young star, still in the earliest stages of formation. If you look closely, you'll see the baby star nestled inside a molecular cloud. The Orion Nebula is one of the closest HII star-forming regions to Earth, which means we can observe stars being born in real time, at cosmic scale. In HH34, the newborn star is ejecting a superheated jet of gas from one of its poles. This gas shoots through space at hundreds to thousands of kilometers per second. Eventually, the jet collides with colder interstellar material, heating it up and making it glow, creating the luminous structures we see in the image. For astronomy, this is a short-lived event, lasting only a few thousand years. A fleeting cosmic birth cry. Number 36, Tauri. Another brilliant pair, this time from the Taurus constellation. These are pre-main sequence stars still pulling in material from surrounding space. Visible to our telescopes thanks to their protoplanetary disks, they offer a glimpse into the earliest stages of solar system formation. In both of these systems, we're not just watching stars form, we're witnessing the likely birthplaces of planets. The dust and gas swirling around them will eventually clump into larger bodies, asteroids, comets, and even fully fledged planets like our Earth. And that means somewhere in the universe, another planetary system might be coming to life. Right now. This next image brings us deeper into the Tarantula Nebula, specifically an area known as NGC 2060. It's technically a star cluster, but unlike dense regions like R136 or Hodge 301, the stars here are much more loosely scattered. In fact, they're no longer gravitationally bound to one another. In just a few million years, the entire stellar group will disperse completely. This region is estimated to be about 10 million years old. But what makes it truly fascinating is what lies at its core. The entire NGC 2060 region is actually a supernova remnant, spanning over 165 light-years across. Scientists believe that a supernova explosion occurred here about 4,000 to 5,000 years ago. Supporting this theory is the presence of a pulsar, a fast-spinning neutron star left behind after a massive star's collapse. This pulsar matches the estimated age of the explosion. But here's the thing, you can't see it with visible light. That's because it doesn't emit in the optical spectrum. It emits X-rays. To detect it, astronomers use telescopes like Chandra X-ray Observatory, which allow us to peer into energetic remnants otherwise invisible to the human eye. If you look at the center of this vast cosmic bubble, you'll find the pulsar, hidden in plain sight. And that bubble? It's the shockwave of the original supernova, still expanding, still reshaping the space around it thousands of years later. A reminder that even in death, stars leave echoes, ripples of energy, radiation, and mystery that can persist for millennia. Light from distant galaxies has shifted, stretched so far into the red that we need infrared telescopes just to detect it. Why does this matter? Because each photon carries energy. The higher the frequency, the more energy it has, and the hotter its source. Lower frequency, less energy, cooler source. That's why we say the universe was once hot and dense, but over time it's expanded and cooled down. This isn't just a poetic description, it's backed by physics. But how does this help us determine the age of the universe? Well, we have to make a few assumptions. The universe is uniformly dense on the largest scales. At first, this seems wrong. There are superclusters of galaxies and huge cosmic voids. But zoom out far enough, and things average out. The cosmos starts to look the same in every direction. This leads to the cosmological principle, the idea that the universe is homogeneous and isotropic on a large scale. The laws of physics are the same everywhere, whether you're on Earth, orbiting a distant exoplanet, or drifting through intergalactic space. Gravity, light, and time behave consistently. The Big Bang happened in all places simultaneously. It wasn't an explosion at a single point. It was space itself expanding. Everywhere, all at once. With these three assumptions in place, scientists can then use redshift measurements and cosmic background radiation to build models of the universe's expansion over time. By comparing the rate of expansion today, called the Hubble constant, to the distances of the most ancient galaxies, we can rewind cosmic history. It's like hitting reverse on a balloon that's already halfway inflated. You can estimate when it must have started inflating. And based on our best data, that number is 13.8 billion years. That's the age of our observable universe, determined not just by light, but by the stretching of light across billions of years. A cosmic timestamp, encoded in every beam of starlight,